Oh, I'll mute you. There you go.
Thank you.
Okay, well, welcome everybody, and thanks for coming to the early seminar. Today we welcome Peter McGill and his team from Forest Livermore National Labs up in North California. And part of the reason for holding this as a breakfast seminar was to allow some of our colleagues in Europe to attend the seminar remotely. So, to introduce Peter, he did his PhD at the University of Cambridge, no less, in the UK, where he specialised in astrometric microlensing, which I think we'll be hearing a little bit later. He confirmed the first white dwarf lensing case. He then moved over to UC Santa Cruz, where he, in an issue that is very close to our hearts here at LCO, he focused on transient supernovae, but also the infrastructure that goes along with building that. And then most recently moved to Lawrence Livermore National Labs, where he has really formed a brand new microlensing group. We are going to hear about more of their work today. So, welcome, Peter.
Thank you very much for the kind introduction. So I'm happy for this to be like, you can interrupt me if you don't understand something. Happy for this to be discussional. I'm come from Lawrence Livermore National Lab. I've got Scott, who's a postdoc here with us, and also Greg Salabry, who's a postbac at Lawrence Livermore National Lab. And then the work that I'm going to show is really a lot of work from previous interns we had. We just had Sophia Kazmarek with us for the summer, but she's gone back to Germany now. And we had James Vardeen last summer, and we also had Abby Kesley-Hung this summer as well, who's now left. And so, we worked with Will Dawson, and then a bunch of people from Berkeley, familiar microlensing faces, and some people from UC Riverside.
Are you unmuted?
I checked the live stream is working.
Okay, so there are. Okay, sorry. There's an IT issue.
We need to check the sound.
No, there are people who want to join the Zoom call, and we're not sharing on Zoom.
Oh, I shared the YouTube.
You just use yes.
That's fine. If they want to talk, they can talk on Zoom, but they can just watch it on YouTube.
Okay, sorry.
We'll tell them to message questions if they like.
Okay, yeah.
No, you're fine.
These are virtual seminars.
Oh yeah.
Go ahead. Sorry.
No worries. Plan. Oh, this is giving up on me. Not activated on mine.
I can start you. Okay.
Does this work now? Excellent. So I'm going to talk a lot about microlensing today. So I know we have some microlensers in the room, but for those who aren't microlensers, I'll just cover some basic microlensing stuff so you all understand what I'm talking about. And then big chunk of the talk is going to be this kind of like high computational cost simulations that we've done at Livermore that have produced a lot of scientific results lately. And then I'm going to move on to this software that we've developed that is a direct result of all of these simulations that we run, which I think is of interest to the people here at LCO, where we can basically classify microlensing events, find black holes in large upcoming photometric surveys like LSST. So very basically, microlensing happens when you have a intervening massive object that comes between you and a distant point source of light. The gravitational field of that object bends the light of the distant background source. And in principle, you can see two effects. So the first one is photometric, so some light that usually kind of goes out this way actually gets deflected by the gravitational field and makes it into your telescope. And so you see the background source get temporarily brighter. And the other effect is astrometric. So because you have this deflection, the source temporarily appears in a different position than what it usually is when the lens isn't there. So if you track the positions and brightnesses of these background sources as they're lensed, you can learn about the mass and dynamics of that intervening object. And so I'll just talk about observable because I'm going to talk about these a lot. So when you have, at the bottom there's an example of a microlensing light curve with an extreme parallax in it. And so if you observe this light curve, you can measure something called the Einstein timescale, which is basically, you can think about that as how long the event is. And so that tells us something about the mass, distance, and velocity of the lens and sources, but nothing directly. The second thing that you can observe is the microlensing parallax. So this shows up as like asymmetric features in the light curve. And this is due to a non-Earth observer moving while the microlensing event happens and changing the relative separation, which kind of deforms the light curve. So you can think of this as kind of like a very weakly to first order, like a measure of asymmetry in the light curve. And then if you have astrometry, you can measure this thing called the angular Einstein radius, which tracks mass and distance. And this is basically, and think about this, about the size of the deflection. So how big that deflection is basically traces the mass and distance, relative distances of the lens and source. So if you want to like find things like black holes, neutron stars, find interesting things, you really need all three of these to basically pin the mass of the lens down exactly, and then, you know, classify it as a black hole or a neutron star or a white dwarf or a star. And that means you need, in most cases, both photometry and astrometry to do this. So up until now, the astrometry part of this hasn't really been possible. So it's kind of easy to do photometry. Well, not easy, I shouldn't say that. There are lots of ground-based observatories that can do photometry and find these microlensing events. We find about 2,000 a year if we look towards the galactic bulge. But astrometry is much harder. You kind of need to be in space for most cases. You need to be able to pin the position of something down to less than a milliarc second, which is incredibly tiny. And so you really need an expensive space observatory. But now we're entering, I think we already are in the era of the golden era of astrometric measurements. I don't think it's going to get better than this. We have Gaia that's just finishing up its decade-long survey of the entire sky. So we have positional baselines for many things in the optical. Roman is going to start up in a couple of years, and that's going to monitor the galactic bulge for 5 years at a 15-minute cadence for photometry and astrometry. So we're going to get the positions and brightnesses of billions of stars at a 15-minute cadence. And then we have, you know, we still have HST for now, where we have James Webb and possibly Euclid as high-performance astrometric instruments that can be used for follow-up. So I don't think it's going to get better than this. It's only going to get worse. So I think, you know, this is a real sort of golden time to be thinking about how to measure these kind of astrometric signals of these things and how to exploit them to increase the yield of interesting lenses and what we can learn. But the microlensing's real niche is its window into the dark and isolated populations of the galaxy. So basically nothing is known about the isolated population of black holes. We expect there to be about 1 billion of them roaming around in the galaxy. We've only detected one by microlensing. And so we don't even have an observational constraint on the number of these, on the abundance of these objects, right? And these are like the endpoints to stellar evolution. They can tell us about the dynamics of the dark matter in the galaxy. And so we basically have no visibility, and microlensing is really the only current way that you can actually detect these things. Same goes for neutron stars. We know a little bit about this population through pulsars, but other than that, that's, you know, a couple of maybe of order 1,000 objects. But these are kind of a weird subset of the neutron stars. So again, microlensing's real power is getting to these dark, isolated populations that we basically, up until now, know really nothing about. So yeah, we don't need any flux on the object that we're studying, and we don't need a companion, right? So this is this isolated part of its niche. But it's not that straightforward. So on the right is a simulation. This is a popsicle simulation from Casey Lamb's work of the simulation of the galaxy, and we run it through. We'll talk more about it later, but we basically project where all the different types of lenses you can have in the galaxy, you look towards the bulge, end up in this observable space. So this is this length of the photometric microlensing light curve. We have to move. And then this y-axis is the microlensing parallax. So you can see that these different types of lenses kind of end up in different regions of the space, but they overlap, right? So it's not entirely, you can't directly say if you measure something with some, you know, TE pi in that overlapping space, it's definitely a black hole, right? So it's this, you get a direct probe of these, you know, nice mass, distance, and velocity relations, but the way that they kind of manifest is this highly confused space that is kind of hard to disentangle and pick apart. So this is a real challenge, is from just, you know, measuring these photometric light curves, we don't actually, you know, get the mass directly out in most cases. It's kind of hard to disambiguate things. And so the photometric and astrometric components of the microlensing signal, you know, they both come from the same underlying phenomena, but they're actually very differently behaved. So for your photometric signal, the length of a photometric event is roughly days, up to a month. can be long in extreme cases, in multiple months, even years. And the signal that you get can almost be arbitrarily large. If you move your lens and source closer and closer together, you can basically increase the signal to an incredibly high amount. And it eventually gets washed out by higher order effects. But there's this nice property that you can probe really small masses as long as you get your lens and source very close. And yeah, this kind of like broad characteristic is when the lens and source are closest, the signal's at maximum. The astrometric is very different. It lasts a lot longer. So for like sub-milliarc second space observatories, at the minimum for like most lenses in the galaxy of stellar mass, they're months, and they can often go on for years, if not decades. And what's very different about the astrometric signal is that it doesn't have this nice, you can arbitrarily grow the size of it if you just have a closer alignment. You're actually fundamentally limited by the size of the angular Einstein radius of the system, which means that it behaves very differently. So you need things with large theta e's to get a detectable signal, very different to the photometric effect. That changes what types of lenses you can probe, how far away they can be, and all of this. And yeah, because of the quirk of the signal, the peak of the signal actually doesn't happen at the photometric peak. It happens offset, so it can happen before and after. So this is actually puts us in a really interesting follow-up regime. We have two signals that don't overlap in time, right? So we can maybe use one to figure out something about the other and about how we allocate follow-up. They're not temporally located together. And also what happens is this gives rise to different detection channels. So the Galactic Bulge Time Domain Survey is basically for the exoplanets entirely focused just on the photometric signal. It's got no science requirements to be met for astrometry. It can do very good astrometry, but it's not in the core science. You can get events that are basically just photometric, which means that they just have a detectable amplification, no astrometry. You can get this overlapping set of events where you can find the photometry and the astrometry. So this is where the first isolated black hole was found in this regime. And you can also get events that are really wide separation and don't have any detectable amplification, and they just have an astrometric signal. So this is the work that I did for my PhD, is we use this channel to basically measure the mass of an isolated white dwarf for the very first time. So these channels are different. They've got different rates. They've got very much different information content. So you can learn different things about the lenses from the astrometry compared to the photometry. Different costs to pursue. Photometry is significantly cheaper than doing space-based astrometry. They happen over large different timescales. And yeah, this leads to different follow-up strategies about how you kind of want to optimize to follow something up and extract the information that you want. So yeah, so now I'll talk about the simulation work that we've done. So that's the microlensing basics covered. So yeah, the thing that we do have at Livermore is nearly unlimited compute. So that gives an excuse to run these large simulations. So we did a lot of work where we ran Popsicle at basically a large scale to simulate the Roman Galactic Bulge Time Domain Survey. So this is a space telescope that's going to give us photometry and astrometry for 5 years in the bulge. So the Popsicle simulation at the top, we take a model of the galaxy, we split it off into components, we evolve those components according to stellar evolution, create black holes, neutron stars, then we inject those into a simulated survey, the Roman Galactic Bulge Time Domain Survey, and then spits out this catalog of simulated microlensing events. And then we can kind of learn what Roman can do, what we can probe. And the other thing, so the main research we're funding on at the moment is Will Dawson's grant at Livermore, which is about probing compact dark matter in the form of primordial black holes. So we also, turned our dark matter in the galaxy into primordial black holes and injected that as well. So we can basically make predictions about what Roman is going to see given this large simulation. So this starting simulation was about 500,000 core hours on our compute. I think we're now approaching nearly 1 million, which is, yeah, it's that's actually an incredibly small ask for Livermore, which is good to know. It doesn't even meet the threshold to asking for extra things at Livermore. It's just so yeah, the first thing I'll talk about, okay, so here's some tracks from the simulation. So this is just the astrometric signal. So we focused at this wide separation regime. So we looked at events that just have an astrometric signal. So all of the simulations before us looked at events that were detectable photometrically. We explicitly excluded those from our simulation. So this is kind of like a new kind of detection channel that we're probing that nobody else has looked at before. So this is just a selection of astrometric tracks. So the blue is what you'd see if there wasn't a lensing event happening. This is just the proper motion and parallax are the background source as it goes across the sky. And then the green is the signal that you'd get from an astrometric microlensing event. And the red dots are the galactic bulge time domain survey 50-minute cadences. And you can see they're grouped into seasons for people that know about the Roman galactic bulge time domain survey. So the thing that was kind of surprising to us is that you can basically pick up things that are Jupiter mass in the astrometry, all the way up to things that are intermediate mass black hole mass. So there's an incredibly large dynamic range of objects that Roman will probe with this astrometric microlensing. You can see that the Jupiter mass objects, the planetary mass objects, kind of have really short signals. So there's red dots 15 minutes. So, you're going to get, it's about an hour, that signal in the data set. So very short. They're going to be easier than the high mass things. And the reason why is you have a clear baseline signal and baseline. If you look at the high mass things, that's the entire 5-year survey. It's going to be all signal. So that makes it hard, right? Because you're not going to see a baseline in the astrometry. You're just going to see the astrometric microlensing event, which is going to make this challenging for a lot of high mass black hole kind of lenses. So yeah, if you just look at, we'll go to primordial black holes and dark matter first. So yeah, if you put all of your dark matter in compact objects, so this is on the plot on the right is just the number of events times the fraction of dark matter. So the way to read that is if dark matter was 1, that's how, if the fraction of dark matter in compact objects is 1, which we know it isn't, that's how many events we would detect. So you can see for a given, monochromatic mass spectrum of primordial black hole dark matter, we're going to detect, we're going to be able to detect many hundreds, if not thousands, of events with Roman. And what's also interesting is that dashed line at the top is the number of astrophysical lenses we're going to detect in this channel. So it's about 3,000, which is more interesting. So Roman's going to have a stream of about 3,000 events over the course of its survey that don't have any photometric amplification. They're just going to be astrometric signals. So all of the work that the galactic bulge time domain survey Roman pits are doing to detect exoplanets, the photometric alerting systems are not going to find these things. Somebody's going to have to go do it. So yeah, back to this space of so now I've shown you spaces for the photometry in timescale and parallax, but for astrometry, you get something different. You can measure theta e. So you can think about where lenses lie in the timescale and size of the astrometric signal. There's a different space that doing astrometry gives you. So what this is just all the different, masses of PBHs in dark matter that we put into the simulation, overlaid on where all the astrophysical lenses lie. So you can see that as we, kind of pop out of the bottom of the stellar masses, our dark matter becomes very detectable and distinct from the astrophysical population. As we go across in mass, it becomes harder to disambiguate between these primordial black holes and this astrophysical population. And again, we can poke out the top with the higher masses. But yeah, this is a really interesting space. Nobody's really thought about it before because we've not had astrometry for lots of events, but it's certainly different to the photometric case. Yeah, so I'll just talk about the conclusions that so this is a paper that James Fardeen was a summer intern led last summer. So we did the star matter simulation, and this is the detectable distances of lenses astrometrically as a function of mass. So if you're not interested in dark matter, you can just think of these as test mass particles, right, in the simulation. And so you can see that where we have low mass, the lenses have to be very close by to be detected astrometrically. And this is because theta e scales with mass. And so if you have a small mass, you've got to bring your lens very close to increase theta e. And you can see as we increase our masses, we can detect things further out. But then something weird happens as we increase our masses to very high stellar mass, 10 solar mass objects, we lose the close things. And the reason why that is because you actually then in that regime, you become dominated by the fact that you need a change in detectable signal within the 5 years of the galactic bulge time domain survey. So remember all those events that were just signal? We need to actually see some detectable change in the signal, otherwise we can't measure it. So you have this weird thing where for small masses, you get everything close by, Then this is the intermediate regime where you can probe all distances. And then as you go out to higher masses like your stellar origin black holes and your ones that are larger than that, you actually are only sensitive towards the bulge. You lose all of the close things because they just don't move fast enough to cause a detectable signal. So you can turn these into constraints on the sort of fraction of dark matter versus mass, monochromatic mass spectrum of the dark matter. So we concluded that Roman is actually going to carve out this novel region of this space. So this should just be readily computable from the galactic bulge time domain survey data. The red is like the pessimistic case where we assume that we can't differentiate primordial black holes from microlensing events in any of the observables, which is not true. And then the black is the most pessimistic case where we assume that we can disambiguate any primordial black hole from astrophysical lens, which is also not true. So we're probably going to lie somewhere in between those things. So yeah, there's potential for Roman to actually produce novel constraints on dark matter from the astrometric processing if it were to be done. And yeah, we end up being entirely limited by the actual duration of Roman, not any of the astrometric properties or the survey cadence. We're actually limited by the 5-year survey, which is also interesting because you can actually extend. So Roman could be up for an extended survey of 10 years if you just revisit the galactic bulge field survey windows once more after 10 years. You increase your time baseline, which is the main driver of detecting astrometric events, significantly. It's like a power of 2/3 you get. So just trivially increasing the time baseline without much effort of Roman could actually open up quite a more massive constraining power.
Just a sec. What are all of the abbreviations on that?
Oh yeah, good.
Right-hand side.
You're going to test me. I know some of them. All constraints of dark matter. So the Milky Way microlensing, that's MWML. So that's Ogle looking towards the Magellanic Clouds. So looking through the galactic halo. M31 microlensing is looking towards M31 and looking for pixel lensing, I think it was.
Mm-hmm.
You've got lensed supernova near the red line. You've got wide binaries. You've got the CMB. And
I use some of those. Some of them are very obscure.
Trying to look it up, but that's slow.
yeah, so these are all the constraints. I
Yeah,
think
but
some of them
like-
have been killed. I think the one star constraint has been killed. It's continually evolving. But yeah, I think the main point is we carve out this nice little notch that happens to be kind of the same notch that Ogle recently carved out with their 20-year survey. So it actually might be a good cross-check of their methods. But yeah, I've yet to digest that paper.
Do you have your own 3-letter acronym to put on this plot?
Maybe, yeah, that's a good point. We should. No, yeah, we should think about that. We just take suggestions. Okay, so onto the more exciting. Well, what I think is more exciting is you can actually look at the yield of astrophysical lenses, so your black holes and your neutron stars. So all in all, stars, everything, we expect to detect about 3,000 events in this channel of just pure astrometry. There's going to be about 300 black holes in there and about 300 neutron stars. So this is things that have no photometric signal, just detectable astrometry. So if you compare that to the yield of events with both photometry and astrometry from the Katie Lamb Roman white paper, it's about the same. So this channel is going to be, in terms of numbers, about as important as the kind of main channel that everybody's considering. If you look on the right, some of this kind of nice thing that we figured out with Abby in the summer is that in this, again, we're in the astrometric space now, this theta E TE. The neutron stars end up in a unique part of this space, the isolated neutron stars, which is very interesting. They don't in the photometric TE pi E. They overlap with the white dwarfs, which we'll talk about later. But yeah, they overlap, and why they are in a unique space, and the reason why they're in a unique space, this unique space, is their kick velocities. So their progenitor kicks, their natal kicks, make them faster for their mass than any other lenses. So with Roman, if we look at events that populate this space, we're probably going to be able to get a constraint on the neutron star abundance and also the kick velocity distribution, which is interesting. It's never really been probed. Yeah, so that's the... Okay, so now that was the simulation stuff. So now I want to talk about the software that we managed to get out. So we did all these simulations. We thought, you know, how can we leverage them for things other than looking at Raman and astrometric signals? And it turns out you can leverage them for classifying black holes in photometric surveys, like what LSST will do. So yeah, as I sort of hinted at before, for a microlensing event, the photometric and astrometric signals are not simultaneous. And you need to measure all three if you want to find your black holes and your neutron stars. And so this opens up like an exciting kind of follow-up space, right? You can imagine detecting something with LSST, the photometric part of that curve, being pretty sure on the parameters as you get down here, right? You're going to get a decent constraint on pi and t when you're down here. And that might give you enough time, if you can classify it as a high confidence black hole, to convince James Webb, Raman, to point at it and catch the astrometric signal before it dies. And if you can do that, you can classify it, you find black holes, you can start to build up a sample of black holes, of isolated black holes in the galaxy. And yeah, so there's this very interesting informational follow-up kind of game you can play. And so yeah, can we exploit this? And the key to really being able to do this robustly and convince a TAC to give you expensive space-based astrometry, right? Is you want a robust measure of the probability that some given event is a black hole, given that you've seen the light curve data. So this is what this package does. Maybe it's the next slide. Yeah. So this pop class, it's on GitHub. It's pip installable. It's not a 1.0 yet, so there's going to be some bugs, but we're getting there. So what this package does is basically it takes in some posterior from your light curve. So if you fit your light curve, you get a posterior on TE pi E. We then have this simulation database of basically simulated where different types of lenses lie in this space, and we can very quickly and scalably connect that to calculating this probability of lens cast given some galactic model and your light curve data. To do some tricks, to do some important sampling, we build KDEs. See on the right this GIF. So this is a posterior. So this is like a range of posteriors. This is a simulation output on the left. So we have a simulation with a set of assumptions, right? We assume some initial final mass relation. We assume some model of the galaxy. We can then generate a catalog of events. We can then turn that into kernel density estimates of where these events lie in the posterior space. And if we convolve our posterior with this simulation, we can actually estimate this probability that the lens is a different class. So you can see as the posterior is buried in the stars, got high probability of being a star. Then as we cross over to white dwarfs pick up, and then if this posterior is in where the black holes lie in this space, we get a confident classification of a black hole. So the one interesting thing to note is, I was talking about neutron stars in the astrometric space. So we're back to the photometric space now. So it's not d to e on the y-axis, it's pi e. You cannot confidently classify neutron stars in this space. They are too much buried in the rest of the distributions. So what this plot doesn't show, because it's hard to show, is we're just showing the where these lenses lie by class, but there's some normalization in here, right? There's many more stars than there are neutron stars and black holes, right? So the actual distributions are different heights, right? But we can't show this because we don't have another dimension. So this gives you I'll show another plot in a minute that'll give a better indication. But yeah, under the hood, for people that are statistically inclined, this is naive Bayes classifier where we built a mixture model from a simulation catalog. It's pretty fast. We've not tried to make it fast yet. It's fast. It takes about a second to classify an event posterior distribution. You have to have the posterior. That takes a long time. But if you have the posterior, about a second, we could make it faster. We're basically limited by how fast we can build a kernel density estimate of the simulation. And it's plug and play. If you can simulate something like on the right, so we can do it with Popsicle, you can basically plug that into the Python package and run classifications given on that. So we have a bunch of preloaded galactic models in there, which you can play with. But if you wanted to run a goal simulation, for example, and as long as you can generate a catalog of events and where they lie in the observable space, it's pretty easy to load it in and basically classify your lensing event. So this kind of plug and play nature allows you to like check about whether or not some of the assumptions that you make in your galactic simulation change the classification. You can kind of like average over them if you want. You can just see how classification changes, kind of flexible. So yeah, this is the classification space for one of the models that we have. So yeah, this is different to the kernel density plot that we just saw, right? This one, because this includes the normalization of stars versus white dwarfs versus neutron stars versus black holes. So you can see with the stars, there's like regions in the top left where you can basically confidently class something as a star if it's up there in TE pi. But for neutron stars, there's nowhere in the space, right, that you can classify them confidently. And luckily for us, black holes, there's a nice blob down the bottom right where if they end up there, you can classify them confidently as black hole. White dwarfs, a bit more tricky, but there are regions like there's this very problematic region here and here. You see there's a boundary where something quickly changes from being a black hole to a white dwarf. So if you've got a high parallax signal along TE, you're in the danger zone. The simulation suggests that it very quickly changes from being a black hole to a white dwarf. So this is the work that Sophia did this summer, so it's going to be submitted soon. We also implemented this non-class, so to make the classifier a bit more robust. Obviously, a galactic model doesn't have to be complete. Popsicle certainly isn't. It doesn't have free-floating planets or brown dwarfs in the simulation, so we don't have visibility into those classes. And so what you ought to do is build some kind of uncertainty quantification that indicates that, which is this non-class. So we've constructed this density, which is basically everywhere where the simulation data isn't. So what that tells you is if your posterior is in a region where we have no simulation data from the galactic model, this class is going to have a high value. So basically just lets you know, kind of like a warning, right? If you have a high non-probability, it means that your galactic model may be lacking, which is, it's common. Depending on the priors that you use for in your light curve, you can end up with a large posterior density in a space that isn't covered by the simulation. So yeah, again, just giving you some sneak previews of stuff that will be in Sophia's paper. So the nice thing about this is some of the other classifiers that the microlensing community develops need very specific things. So I think the sort of kind of state of the art is this dark lens code that I think a lot of people have been involved in developing. You kind of need proper motion estimates of the source from Gaia. You need like a strong parallax signal for it to work. With this, with our classifier, you basically just need a posterior on TE pi. You don't, well, on any observable. You're not stuck with TE pi. You could just classify on T if you wanted. But you don't even need a constraint. Like if your posterior is diffuse, the framework still works. So you can see here these examples. The posterior in pi is kind of diffuse, right? It's hard to constrain this, but we can still classify it. And so we just run this over all of the OGL 3 and 4 data set because we don't need any special things. We just need posterior distributions on the light curve parameters. So it's pretty easy to just run over large sets of microlensing events. And you can see, here's just 2 example candidates where we can confidently classify them, in the 80% of being a black hole, which is kind of interesting because these events overlapped with Gaia. They were, obviously we can't go after, they're at 2017 or something, the time of maximum. So obviously the astrometric signals died for these now, but Gaia might have seen something. That's interesting to look at these things that have long gone back down to baseline. Yeah, that's it. I'll just leave my summary up. Thanks for listening. Yeah, happy to take questions.
Thank you very much, Peter, and open for questions. April?
So at the beginning, you were talking about, pardon me, you were talking about microlensing. What, if anything, distinguishes microlensing from gravitational lensing?
This is a good question. My understanding is I read some of this history of how it was named when I was writing the introduction in my PhD, and it's classically it was the fact that you couldn't resolve the images. So in general strong lensing, you can, like in gravitational lensing, like with galaxies and stuff, you can usually see your images, right? Or you can see some like perturbation of something. And whereas in microlensing, the images are the two images that are produced. Should we go all the way back? Yeah, so the separation between these two things is usually too small to be resolved by your telescope.
So
You
you're
see a blob of light.
getting like those infamous Einstein rings. It's a
No, we can't see that. Well. In 2019, somebody did see one. They used, was it interferometry? Was it interferometry? Yeah, they were able to resolve it because these like a milli arc seconds.
Yeah.
What microlensing isn't is microlensing doesn't refer to the micro arc second scale. A lot of people think that's not true. It was never that. But yeah, these things are breaking down as like telescopes get better, techniques get better, we can resolve these. And for astrometric events, they're actually large enough, like an event like this, the white dwarf that we got, we could actually resolve the lens and source for the duration of the event, because the astrometric signals detect at a lot larger separations, so we could actually resolve everything. So it was actually kind of like more like a weak lensing measurement than a microlensing measurement.
so microlensing can't be resolved usually just due to like the strength of the lens, like how massive it is.
How close the lens and source have to be. So they have to get pretty close. They have to get within like milliarc seconds of each other, maybe even microarc seconds. Yeah, because the lensing involved with like, your classic gravitational lensing with galaxies, right? You've got millions of solar masses of mass, so they can be kind of well separated on the sky. Whereas you get onto microlensing, you're dealing with things that are like a solar mass. So they have to get really close together for the effect to be detectable, which means by definition, it's hard to resolve them with your telescope.
Thank you so much.
Anyways.
I mean, there is also the time scale. Like the Einstein cross will not change for many, many, many years. They move very slowly relatively to each other, and microlensing can, in a couple of years, the event is gonna be like long gone. You will be able to separate the source and the lens.
Yeah, that's a really good point.
Yes.
Microlensing is in the time domain. That's a good point.
Yeah.
What prospects are there for improving the galactic model and therefore the posterior distribution when Gaia reaches the end and we're on DR final, whatever number that turns into?
Yeah, there's plenty of room to improve simulation. I actually, we're doing a lot of work where we're trying to basically, Scott's leading this effort, right? We're trying to infer properties about the dark matter in the galaxy. And we are finding that we're simulation limited at the moment, right? Our simulations are just not good enough we're not data limited, we've got plenty of data. But yeah, so I think, when Gaia finishes and we have, better dynamical maps, it probably is worth visiting and trying to improve these galactic models, because I think it's going to fast become the limiting part of figuring out anything about these isolated populations. So yeah, I think there is a lot of scope to improve these galactic models, especially with stuff like the Gaia data. Yeah, I think it's fast going to become a problem. I think it already is a problem. I think we think it already is a problem.
It's a for our dark matter work because it's a systematic, but very exciting for the galactic model work. It seems like we can actually say something statistically significant. Hopefully, we're in the final stages of that paper, but it does seem like there's enough information content in the data to discriminate between some of these kind of broad. I mean, we're not measuring angles of the galactic bar, but we are kind of probing different IFMRs for black hole creation. We're probing neutron star kicks. The average neutron star kick seems to be something that we're sensitive to. So it's exciting.
Yeah. And as well, like the reason why getting a full galactic model so hard is because they're often disjoint, right? For example, Popsicle, really good on black holes, neutron stars, right? But obviously lacking in free floating planets, brown dwarfs, right? It's because there's a team with an expertise that builds something in, right? And then goals, good free floating planet support, but no black hole support, right? So it's hard. I will say for classification, because we have built this in catalog space, we could actually, in theory, concatenate a goal simulation with a popsicle simulation and have everything for classification because we're in catalog space. All we require as input is like an input catalog. As long as you're consistent about what you call a microlensing event, there's no reason why you couldn't easily concat gulls and popsicle together for classification, for example.
It's a linear model. So
I may jump in. What possibility is there to provide ancillary data to help to shape the posterior probability? So say like you have an independent constraint from, say, photometric constraint on the distance to the source. Presumably that then impacts your posterior probability. Do you have the capability to feed in that information where available?
Yes, but in a specific way. So the general rule of thumb is if you want a constraint on something, if you want to use that in the classification, you ought to be able to simulate it. So as long as your simulation space includes those things,
Okay.
and you have a constraint on them,
Yep.
this classifier will work. So we're flexible about, we're not requiring that a simulation has any particular thing, but if you put in the distances to the sources, and then basically you can combine your TE, pi E posterior with some constraint posterior on the source distance and feed that all in. And as long as you have that simulated in your galactic model, it all connect together.
I'm thinking particularly for, say, LSST, where we won't get astrometry, but we will
Right.
get very good photometry in multiple bands, and
Mhm.
presumably you could pre-calculate then for each potential source star. You could
Yeah.
give a distance and spectral type estimate.
Yeah.
Which could be then in fact into your database.
Yeah,
Is that
absolutely.
something you have the capability to do, or you're developing?
Yeah, so again, the software package, we've packaged some models that we have, but we have the ability for users to contribute a model.
Mhm.
And so as long as you can simulate it, as long as it's a Monte Carlo simulation of some parameters that you then have a posterior constraint on, the framework will work.
That feels like something we should talk more about this
Yeah,
afternoon.
I think so.
Any other questions?
I have one, but maybe
Go
it's,
ahead.
so you mentioned that there's going to be a population, or there may be a population observed by Roman of intermediate black holes who have astrometric signal, but they don't have long enough baseline. Is it possible to stitch like previous astrometric surveys, for example, I mean, Gaia or some like fields from HST, and like create an artificial baseline for those?
In principle, yes. In practice, hard, right?
Yeah.
So first off, HST. I mean, the general rule, right? If you ask, has HST observed a patch of sky? The answer is no, because the field
Yes.
of view is so small,
Yes,
right?
exactly, yes.
So like, there's probably not. Well, I don't know. There was these Treasury bulge programs, right? Maybe.
Mhm.
Yeah. Other thing is, obviously Romans in the near infrared. Right.
Yes.
So all of these numbers are in the near infrared, so we're piercing the dust. Whereas Gaia, right? Gaia's missing like, if you like
yes.
yeah, if you compare like the VVV, which is ground-based near infrared, with Gaia's missing like 500 million sources in the bulge.
Yes.
So yes, for some events where we have an optical,
Mhm.
strong optical in the optical passbands where we can get a decent measurement, yes. But I would guess for the most part you need space-based near infrared astrometry to build a good baseline, which
Well,
is, I don't think there's some kind of efforts to try and, James Webb could collect this.
Mhm.
Euclid might be able to collect it. I know they're interested in doing like proper motion astrometry, but again, you could look at baseline stuff. Yeah, but again, there's no requirement to collect it before. There might be, but I can imagine a tax saying, you should just collect this after, and then why not just have Roman do it at the end of 10 years? Right. So yeah, it's hard to make that case that it's got to be a case where you learn something from being able to react to it being a black hole, right? So if you have this photometric component as well, and you can convince attack that you're gonna need to know that it's a black hole in real time to like constrain its properties better, then maybe you could argue for like a pre-cursor survey to Roman, but we're running out of time, right? Roman's launching next year.
Yes.
I mean, to pin parallax, right? You're probably going to need at least a year or half a year, probably half a year actually, to get the parallax acceleration pinned.
Yeah, and like the argument would be also that in order to like even know that such event exists, is that you need some baseline to see the difference. So actually, it does make sense to do it before Roman.
Yeah.
Maybe 10 years is not going to be enough. Maybe you need like a 15-year.
Yeah, and as it stands, Roman's not going to do any. Still being decided, but there's not going to be any real-time astrometric processing of the data.
Yes.
There's also a wide field science call coming in next year, so maybe it's a good thing to suggest. But yeah, as it stands, the Roman team are obviously focused on the exoplanets, which is photometry only, right? They have to deliver those things, so there's not the bandwidth to consider anything other than getting the photometry really good. But I think there's going to be some kind of light astrometric processing, which is like, here is the very loose position, maybe a proper motion, who knows? But nothing beyond that. They don't have the compute or bandwidth to do it. And yeah, we could get things like, I think there's scope to lobby that team to provide us astrometric indicators like what Gaia has, like the Ruve, which they could compute something very easy that tells us if there's some astrometric anomaly happening with the event, right? Which then might allow you to go into the data set and do a full astrometric reduction, right? I think there's scope to lobby the people that are doing this, building these pipelines, to kind of include that information, which would be very helpful to kind of like, picking out something that you want to spend a lot of time and resources on reducing astrometrically. So I think there's scope to try and like persuade the Roman processing teams to like give us things that are useful. But my understanding is that there's no real scope to actually get them to do any kind of astrometric processing. That has to be argued for and won, maybe on a wide field science call or something.
Picking up on that, the actual positioning of the Roman bulge time domain survey field is possibly not ideal for what you're trying to do. I mean, yes, okay, it's in the infrared, it sees through a lot of the dust, but it's still looking slap bang into the middle of the galactic plane in the bulge, where you're not going to see that far into the other side of the galaxy.
Yeah.
You had a graphic up earlier in the talk where you had a column density going almost through to the other side if you look slightly out into the plane.
Mhm.
And Roman has just created a plane survey committee that you should probably
Yeah, probably.
and it sounds like astrometry would be a very powerful addition to that.
Yeah, absolutely. Yeah, as soon as you open up the area, astrometry is nice because you don't need high cadence for,
Exactly.
right?
Yeah.
So if you open up the area and just visit it monthly, twice yearly even, you're going to find a lot of things.
I mean, the available time for Roman that isn't the other three surveys is not high, but you could envision, say, a pencil beam at certain areas in the galactic plane where you just revisit it more often than in this canonical survey. That is something that we should really follow up with.
And there's also the case of, right, like the white dwarf that I went after in my PhD, right? There's one of these very close by, well, I don't know where I'm going. Yeah, this regime. One of these very close by lenses where the lens exists, it's proper motion. So somebody could just take all the white dwarfs in front of the plane, check whether or not they're going to cause an event during Roman, and then you have an incredibly targeted ask of like, observe this. There's no risk, right?
Yeah.
You can like point at all of these white dwarf targets and just get astrometry for them. But it depends, the scientific impact of getting the mass of a white dwarf, right? It's there are other ways to get masses of white dwarfs. They have to be in a binary system, but like I had a rough time like convincing the white dwarf community that this is like an important thing to do. Like it's very expensive. It might not be expensive if Roman does something, right? But in the regime that we're in, which is like trying to win, like 15 orbits of HST to do one object, it's a hard ask, right? So when I went to, share this result with the white dwarf community, I was like, this was really hard and took a really long time. Do we need more of them? Right? And the answer was like, maybe. So like it's connecting the white dwarf more, because there's loads of interest in physics, right? You get to model degeneracy physics, atmospheres of white dwarfs. People are now finding planets around white dwarfs, right? I think there's a case to be made, but it's just like getting the finding the right science angle to make it compelling, I think. There's also a kind of a niche lab element to this. So we have NIF, right? We have the National Ignition Facility. We can simulate the conditions in the center of a white dwarf at NIF. People have done that to get the equation of state. And that's hard. If you could convince somebody that you could connect observational astrophysics to experiments in NIF, that's like a very fruitful path to go down in the lab. Like they invest heavily in NIF. So there's that angle. I've done it before. There's a Nature paper where they simulated the conditions of a white dwarf at NIF. It was like 5-6 years ago. I think that science has kind of died now, but if you could convince them that they could test some of these lab constraints with like observational astronomy, there might be an avenue there. But yeah, it's the right science angle. Compelling science angle is tough.
Very interesting. Any other questions? In that case, let's thank Peter again.
Well, sorry, one quick note. Say Peter is biased because he loves microlensing. For the non-microlensers, the software that we're working on is completely generic. The only thing that makes it microlensing focused is because we're pre-packaging it with our own simulations.
Mm.
If you want to bring your own simulation to the table and you're interested in fully Bayesian classification with noisy estimates in the context of a population model, we should talk. It's very general. And so if that's something you're interested in, we'd love to talk about it.
Oh, so in principle, you can use it for transits, I don't know, whatever.
Exactly.
Because
Anything you have a population model, you have
Oh, so,
unobservable.
okay, yeah, so it doesn't even have to be like a galactic thing. It can be solar science or whatever.
Yep, it's completely, it's very generic,
Mhm.
kind of statistically defined in terms of relating noisy observations to some hierarchical model. Yep, thanks.
Recipe.
Much new.
Yes.
Yeah, it was fun. And Greg did
A little bit.
pretty much